This wireframe represents a relational database node under maximum load. While optimized for complex queries, baseline throughput is physically bounded by disk I/O performance. Beyond storage limits, these engines are stateful. Because each connection requires a dedicated backend thread, maximum concurrency is capped by the server's available CPU and RAM. Scaling modern cloud applications past these hardware constraints requires moving away from standalone instances to engineer a multi-tiered data layer. We will construct this layer across 3 tiers: cryptographic security boundaries, connection proxying for serverless scale, and in-memory caching fabrics for sub-millisecond read latency. Achieving enterprise scale relies on combining these services to offload the inherent physical constraints of the relational engine. Securing a database begins at the physical storage layer. Amazon RDS and Aurora use AWS KMS to apply AES 256 encryption, transforming data blocks into ciphertext. This KMS protection extends to the primary volume, automated backups, manual snapshots, and read replicas derived from those snapshots. Note the strict operational constraint. Encryption must be configured at launch. You cannot toggle encryption on for an already active, unencrypted database volume. Securing an unencrypted volume requires a 3-step migration. First, execute a manual snapshot of the instance. Second, copy that manual snapshot while applying a KMS key to encrypt the copy. Finally, restore a new encrypted database instance from that protected snapshot. KMS encryption provides a robust storage boundary, but implementing it on existing volumes requires these specific infrastructure workflows. For data in flight, RDS and Aurora enforce TLS by default. To secure the network handshake, client applications should utilize the official AWS root certificates. Even with an encrypted tunnel, static database passwords stored in application configurations remain a vulnerability for credential leakage. To eliminate this risk, you can transition to IAM database authentication. This diagram shows the cryptographic exchange. Instead of a password, compute instances use IAM roles to generate a temporary authentication token, bypassing traditional password prompts. These tokens have a strict 15-minute lifetime, which mathematically narrows the window for potential credential misuse. Combining KMS storage encryption, TLS transport, and short-lived IAM tokens creates a zero-trust boundary around the database engine. Security is only half the battle. Highly concurrent transient serverless functions like AWS Lambda create a massive operational bottleneck for stateful databases. During traffic surges, hundreds of functions spin up simultaneously. Each one creates a dedicated backend thread, rapidly exhausting the database's CPU and maximum connection limits. Amazon RDS Proxy resolves this by sitting within the private VPC to intercept these concurrent requests. The proxy maintains a persistent pool of established connections, multiplexing hundreds of transient Lambda requests across a small number of optimized database threads. This pooling allows the database to support a 10-fold increase in connections without hardware upgrades. Additionally, if the primary node fails, the proxy instantly reroutes traffic to a standby while preserving active client connections. RDS Proxy also centralizes security by enforcing IAM authentication and retrieving physical credentials directly from AWS Secrets Manager. This proxy architecture effectively decouples the hyperscalable serverless compute tier from the physical connection limits of relational storage. To reach the next level of performance, you must bypass disk I/O entirely and target sub-millisecond query latencies. Amazon ElastiCache provides this managed in-memory layer. Unlike the transparent RDS proxy, implementing ElastiCache requires specific application code changes to handle the caching logic. In the database caching pattern, applications query ElastiCache first. If data is present, a cache hit, it returns instantly in sub-milliseconds. On a cache miss, the application queries RDS, writes the result into ElastiCache for future use, and returns it to the user. A second pattern is the user session store. Active login states and shopping cart data are written directly into ElastiCache instead of the relational database. When a load balancer distributes requests across EC2 instances, any instance can retrieve that session state from the central cache. This pattern renders compute nodes stateless, allowing the infrastructure to scale dynamically without losing user session data. Caching introduces a complex engineering trade-off, ensuring data consistency and avoiding the delivery of stale data. In lazy loading, data is written to the cache after a miss. If the database updates directly, the cache goes out of sync, serving stale data. To fix this, apply a time to live, or TTL. This timer evicts the old key, triggering a fresh database fetch. Contrast this with write-through caching. Here, every application write simultaneously updates both the database and the cache, ensuring high consistency. This consistency comes at the cost of increased write latency and the potential to saturate cache memory with data that is never read. Database architects must carefully choose a pattern that balances specific data consistency requirements against their write latency performance targets. The final decision for ElastiCache is selecting the engine architecture, which dictates your high availability and clustering options. Redis is a durable, feature-rich engine. It supports multi-AZ auto failover, snapshot persistence, and can scale up to 90 shards in a single cluster. Redis also supports advanced data structures. You can use sorted sets, for example, to manage real-time leaderboards directly within the database engine. Memcached is a multi-threaded engine designed strictly for simple key-value lookups. It is exceptionally fast, but lacks native replication. Because memcached is ephemeral, a node failure results in permanent data loss for that specific shard. Use Redis for durability and complex logic. Reserve memcached for high-concurrency, disposable lookup caches. Effective cloud architecture relies on stacking specialized database services. This starts with a resilient storage layer at the base. Amazon RDS and Aurora provide the foundation, offering synchronous replication and self-healing fabrics for disaster recovery. The middleware tier, managed by RDS Proxy, establishes a VPC boundary that absorbs connection spikes and multiplexes traffic to protect the underlying database. ElastiCache caps the stack as the performance tier, providing the sub-millisecond read offloading and stateless session management required for horizontal scaling. Securing this stack requires a unified strategy of KMS storage encryption, TLS data in flight, and short-lived IAM authentication tokens. By coordinating these managed services, architects can build data layers that balance rigorous security and massive concurrency with the performance of in-memory speed.